The object in your hand. You pick up the glass from the table and feel its cool surface against your fingers. It has weight. It has edges. It feels completely solid. Your thumb presses against it, your fingers close around it, and the glass simply holds its shape. You have done this thousands of times without giving it a second thought. Try something stranger. Push your fingertip toward the glass. You cannot pass through it. The surface resists you immediately. The same thing happens with the table beneath your hand, the spoon in your kitchen, the phone beside you, and even the chair supporting your weight. Everything around you seems solid because, at the scale of your everyday life, it is. But there is something you cannot see.
The glass in your hand is not a continuous, featureless block of substance. Neither is your hand. Neither is the table. Beneath the surface your senses can detect, an astonishingly different world is unfolding. One where particles do not behave like tiny versions of the objects you see around you. And this is where your intuition begins to fail. You were taught that an atom has a small nucleus in the middle, with electrons moving around it like miniature planets. It is a useful picture for getting started. But if you take that picture literally, you quickly run into problems that become impossible to ignore. Because the very thing you are holding right now depends on rules that are far stranger than that image suggests. The solidity beneath your fingertips is the visible result of invisible quantum behavior happening continuously, at a scale your eyes cannot reach. And once you understand what is actually happening inside an atom, even an ordinary glass in your hand starts to look completely different. The object has not changed. Your picture of reality has not. The atom you think you know. That familiar picture is hard to forget. You see a tiny nucleus at the center, with electrons circling around it in neat paths, much like planets moving around the sun. It is simple, memorable, and useful for introducing the basic idea of an atom. But there is a problem. If you take the picture literally, it starts telling you things that nature does not actually do. An electron is not simply a tiny ball following a fixed track around the nucleus. There is no miniature road inside the atom. And although you may have heard that an atom is mostly empty space, that phrase can also create the wrong impression. Empty, in the everyday sense, suggests nothing is happening there. The interior of an atom is governed by quantum states and electromagnetic interactions that determine how matter behaves. Even the nucleus is not a little solid marble sitting inside a hollow container. It is an extraordinarily compact system of protons and neutrons bound together by powerful interactions. So the picture you learned was not useless. It was a doorway in textbooks. The mistake comes when you forget that it was only a doorway. And here is the part almost nobody sees coming. The evidence for the stranger picture is not hidden in some distant laboratory. You are already surrounded by it. You are holding it, walking through it, sitting on it, and living inside it every second. The real question is not whether atoms exist. We know they do. The deeper question is what an atom is actually doing when no one is looking at it. Because once you remove the tiny solar system picture, you are left with something much more surprising. And before we replace that picture, there is a reason so many explanations keep using it for decades. Stop imagining tiny solar systems. The problem is not that you have seen those pictures before. You probably have. Colorful animations show electrons racing around a nucleus in neat circular paths. And after seeing that image enough times, it becomes impossible not to imagine an atom that way.
That picture can be useful. As a first introduction, it gives you a sense that atoms contain a nucleus and electrons. The trouble begins when a teaching picture quietly becomes a claim about what nature is literally doing. The popular version says the electron travels around the nucleus along a fixed path, like a planet around the sun. The scientific version is different. An electron in an atom is described by a quantum state, represented by a wave function. That description tells you what outcomes you can expect when the electron is measured. The popular version also suggests that an electron is a tiny object with a definite location moving through space at every moment. Quantum mechanics does not give you that classical picture. It gives you probabilities for where a measurement may find the electron.
And there is another important distinction. The atom is not simply a miniature solar system. Its structure emerges from quantum mechanics and electromagnetic interactions working together. I find this frustrating because the simplified picture is often presented without explaining where it stops being useful. You were not wrong to learn it. You were given a model that was designed to make an enormous subject approachable. But a model is not the thing itself. That distinction mattered deeply to Richard Feynman. His style of teaching physics was built around refusing to hide difficult ideas behind comforting imagery. He pushed toward the mechanism, even when the mechanism was strange. And that is the standard we need here. There is no need to turn quantum physics into magic, mysticism, or vague talk about mysterious energy. The real science is already strange enough. If the familiar picture is only a model, then the next step is to find out what the atom is actually doing, and why the evidence forces us to think about it differently. Learning the mechanism. That is the approach we take here. Complicated science should not be turned into something mysterious just to make it sound impressive, but it should not be flattened into inaccurate metaphors either. If you enjoy understanding why something happens, rather than simply being handed a surprising fact, you will probably feel at home here. We look at atoms, gravity, light, aging, and the human body by following the mechanisms step by step until the conclusion makes sense on its own. You do not need a physics degree to follow this. You only need the willingness to slow down and look closely at ideas you may have encountered before. And sometimes, the most fascinating discoveries are hiding inside things you thought you already understood. That is exactly what is about to happen with the atom. So let's stop looking at it from the outside and follow the chain of physics that actually holds it together. What is actually happening inside? To understand what an atom is doing, start with the smallest central piece, the nucleus. It sits at the heart of the atom and contains protons and neutrons. Protons carry positive electric charge. Neutrons have no net electric charge, but they contribute most of the remaining nuclear mass. The scale is difficult to imagine. A typical atom is roughly 10 to the power of minus 10 meters across, while its nucleus is roughly 10 to the power of minus 15 meters across. In diameter, that is a difference of about 100,000 times. The nucleus is extraordinarily small compared with the atom as a whole, yet almost all of the atom's mass is concentrated there. Already, the old picture begins to crack. If you imagine the atom as a miniature solar system, you might expect the electron to behave like a planet. It should have a path, a position, and a speed. More importantly, because the electron is negatively charged and the nucleus is positively charged, classical electromagnetism gives you a serious problem. A charged particle moving in an orbit should radiate electromagnetic energy. As it loses energy, its orbit should shrink. Eventually, the electron should spiral into the nucleus. But that does not happen. Ordinary atoms are stable. The chair beneath you does not collapse because its electrons are continuously falling into its nuclei. The glass beside you does not suddenly disappear into a microscopic pile of charged particles. This was not a small disagreement between theory and observation. It was a fundamental problem. Classical physics appeared to predict an unstable atom. Quantum mechanics changed the rules. Instead of allowing an electron to have any arbitrary energy and any arbitrary orbit, quantum mechanics describes electrons in atoms as occupying specific allowed quantum states. Think of these states not as tracks through space, but as complete physical arrangements with particular energies and probability distributions. Hydrogen gives us the cleanest example, because it contains one proton and one electron. Its lowest energy state has an energy of about minus 13.6 electron volts, measured relative to the conventional zero used when the electron is completely separated from the proton. That number is not merely a label. It tells you that the electron cannot simply slide continuously down to some lower classical orbit. There is a lowest allowed state.
And this is where the story becomes much stranger. The electron in that lowest state is not simply a tiny ball moving slowly around the proton. Quantum mechanics describes it with something called a wave function.
The word can sound mysterious, but the idea is more practical than mystical. A wave function is a mathematical description that lets physicists calculate the probabilities of different measurement outcomes. It does not function like a photograph of an electron. This distinction matters. When you see an illustration of a glowing cloud around a nucleus, that cloud should not be imagined as a little fog made of electron material. It represents probability density, regions where the quantum description gives you different likelihoods of detecting the electron when you perform a measurement. Those familiar shapes are called orbitals. An s orbital, for example, has a different spatial pattern from a p orbital, and d and f orbitals introduce still more complex patterns. They are quantum states, not miniature racetracks. So the electron is not hiding somewhere inside a cloud while we simply wait to discover its secret classical path. The quantum description itself is different from the classical description. Now consider energy. An atom cannot generally possess just any energy you choose. Its electrons occupy allowed energy states. When an electron moves from one allowed state to another, the atom can absorb or emit electromagnetic radiation with an energy corresponding to that difference. This gives us one of the most beautiful connections in physics. Energy difference produces a photon, and the energy of that photon is related to its frequency by a simple equation, E equals hf. Here, E is the photon's energy. H is Planck's constant, approximately 6.626 times 10 to the minus 34 joule seconds, and F is the frequency. You do not need to memorize that equation to appreciate what it means. A change inside an atom can become a measurable piece of light. That is how we get atomic spectra. When scientists examine the light emitted or absorbed by atoms, they find specific frequencies rather than a completely arbitrary rainbow of possibilities. Those spectral lines are fingerprints of the atom's allowed energy structure. And this is where the theory earns its authority. Physicists are not saying atoms probably work this way because the picture looks convincing. The quantum model makes precise predictions, and experiments repeatedly test those predictions. Spectroscopy lets scientists infer what is happening inside atoms without needing to watch an electron travel along a tiny circular road. The atom is revealing its internal structure through light. But light is only part of the story. The reason electrons remain associated with the nucleus is the electromagnetic interaction. The negatively charged electron and positively charged proton attract each other through electromagnetism. The magnitude of the elementary electric charge is about 1.602 times 10 to the minus 19 coulomb, with the electron carrying the negative sign and the proton carrying the positive sign. In a classical description, you can think in terms of an electric field connecting charged objects. That picture is extremely useful. At a deeper level, modern quantum field theory describes electromagnetic interactions through the electromagnetic field and its quantum excitations, including photons. That does not mean you should imagine tiny visible lines filling the atom. Field language is a mathematical and physical framework for describing interactions, not a photograph of what the inside of an atom looks like. There is another puzzle. If electrons can occupy quantum states, why do all the electrons in a complicated atom not simply pile into the lowest energy state? The answer leads us to one of the most important rules in all of quantum physics, the Pauli exclusion principle. Electrons belong to a class of particles called fermions. Identical fermions cannot occupy the exact same quantum state. In practical terms, electrons in an atom must be arranged among different allowed states. And that rule has enormous consequences. It helps create the layered electron configurations that distinguish one element from another. Change the number of protons, and you change the element. Change the number and arrangement of electrons, and you change how that atom interacts with its surroundings. Now the chain begins to come together. Quantum states determine which electron arrangements are possible. Those arrangements influence how atoms interact. Atoms can share or transfer electrons, producing chemical bonds. Bonds produce molecules.
Molecules form materials. Materials become the glass in your hand, the metal spoon in your kitchen, the wood beneath your chair, and the countless structures surrounding you. The world you experience as solid and ordinary is built from rules that are anything but ordinary. And notice what has happened. We began with a nucleus, only about 10 to the power of minus 15 meters across. We moved through electromagnetic attraction, quantum states, wave functions, energy levels, photons, spectroscopy, and the Pauli exclusion principle. Each idea answered a problem created by the one before it. Even the speed of light, about 3.00 times 10 to the 8th power meters per second, enters this broader framework because electromagnetic radiation carries energy and information between physical systems. Yet none of these numbers is the real lesson. The real lesson is that an atom does not need to resemble a machine made of miniature parts in order to have structure. Its structure comes from relationships. The nucleus supplies charge and mass. Electromagnetic interaction connects the charged components. Quantum mechanics determines the allowed states. The Pauli principle organizes electrons into distinct configurations. Those configurations determine chemistry, and chemistry gives rise to the materials you touch every day. Your hand, the table, and the glass have not become less real because their microscopic description is strange. They have become more understandable. The picture is useful, but only if you remember what it represents. Otherwise, your mind rebuilds the very miniature solar system quantum mechanics forced us to abandon. And yet, there is one trap waiting for you. After seeing an orbital diagram, it is very easy to take that beautiful probability pattern and quietly turn it back into a physical object moving through space. That is where most explanations go wrong. The orbital is not an orbit. The trap is easy to fall into because the picture itself invites you to do it. You see a beautiful three-dimensional orbital surrounding a nucleus, and your mind naturally turns that shape into a path. You imagine an electron traveling around inside it, following some invisible route. But that is not what the orbital means. The version most people have heard is simple. The electron is somewhere specific, moving along a particular path, and we simply do not know exactly where it is. Quantum mechanics gives you something fundamentally different. The orbital describes a quantum state and its probability distribution, telling you what outcomes you can expect when the electron is measured. That distinction is enormous. You are not foolish for picturing a tiny particle following a route. Human perception is built around objects, positions, and movement. When an unfamiliar three-dimensional pattern appears on a screen, your brain naturally translates it into something familiar. But the scientific description does not require that hidden classical trajectory. And the same correction applies to the phrase empty space. Inside an atom, you should not imagine a hollow little container where absolutely nothing is happening. Electromagnetic fields and quantum interactions provide the framework that determines how the system behaves. Once you see the orbital correctly, several puzzles begin fitting together. Atomic stability makes more sense. Spectral lines make more sense. Even the structure of chemistry begins to look less mysterious. The picture has not become less useful. You have simply learned how to read it. But there is an even deeper misconception underneath all of this. What does it really mean to say that an electron exists in a quantum state? The atom is not a tiny machine. You've probably spent your entire life assuming that anything real must behave like a smaller version of something familiar. A ball has a position, a planet follows a path, a machine has parts moving in predictable ways. That expectation makes perfect sense. Classical mechanics works remarkably well for the world you can see. It lets engineers design bridges, predict projectiles, describe planetary motion, and build machines with extraordinary precision. But its success has limits. The version you have been told is that atoms are miniature solar systems. What the research reveals is different. Atoms are quantum systems governed by quantized states, electromagnetic interactions, and quantum statistics. The shift began with discoveries that classical physics could not explain, and the development of quantum mechanics provided a framework that could. The Schrödinger equation describes allowed quantum states, while spectroscopy reveals those states through measurable patterns of emitted and absorbed light. This is not simply philosophy, it is experimental science. Institutions such as the National Institute of Standards and Technology use atomic measurements and spectroscopy in precision science because these quantum behaviors are predictable enough to become practical tools. And that gives you permission to release the tiny machine picture. You do not need to imagine an electron secretly traveling along a microscopic road. You need to understand what the theory predicts, what measurements reveal, and why those predictions keep working. Once you do that, the atom becomes stranger, but also clearer. So, after all this theory, what should you actually picture when you imagine an atom? How to picture an atom correctly. You now have enough pieces to replace the old picture with a much better one, and you can do it with 4 simple ideas. First, start with the nucleus. Picture an incredibly small central region containing protons and neutrons, where nearly all of the atom's mass is concentrated. Second, do not draw electron tracks. Instead, think about quantum states and probability distributions. An orbital is not a road through space. It is part of the mathematical description of where measurements are more or less likely to find an electron. Third, think in energy levels. Electrons occupy allowed quantum states rather than sliding continuously through every possible energy. Fourth, connect changes in those states to photons. When an atom moves between allowed energy levels, it can absorb or emit electromagnetic radiation corresponding to the energy difference. Now try a 30-second mental exercise. Look at an object near you. Instead of imagining millions of miniature solar systems, picture quantum systems whose collective behavior produces the material properties you experience. The object remains familiar, but your explanation of it becomes deeper. You can use this mental model whenever an atomic diagram appears, and it will keep you from confusing a visual aid with literal microscopic machinery. No medical treatment is being recommended here, and if a health video ever discusses changing medication, exercise, diet, or treatment, especially with hypertension, kidney disease, or heart failure, talk with your healthcare professional first. Every spoon, window, table, and phone becomes a reminder that the world you experience is built from rules your senses were never designed to see directly. You do not need to visualize those rules. You need to remember the distinction between the picture and the physics behind it. The next time you touch something solid, remember what is underneath that familiar surface. The object is still in your hand. Think back to that moment we started with, when you held the glass and felt its solid surface beneath your fingers. The glass has not changed. Your understanding of it has. Every morning, every day, every time you touch a table, open a door, or hold a cup, quantum rules are quietly shaping the matter around you. You cannot see those interactions directly, but they are there, constantly. And once you begin seeing ordinary matter this way, an entire universe of familiar things suddenly becomes worth questioning. Keep questioning. If this kind of explanation is useful to you, consider staying with us. That is what this channel is built around, taking familiar questions seriously, following the evidence carefully, and discovering that the universe becomes stranger, not less understandable, the closer you look.